that's not familiar with it. Let's say, so this is special to the United States healthcare system, but let's say you get hurt. And so you go to your doctor. Your doctor takes a look at what happened and they say, hey, you've got to go to the hospital, you need surgery. So you had like a really bad break or something. When the doctor says you have to go have surgery, you can't just go have surgery. It's expensive, it's risky. Your health insurance company wants to sign off first. So your doctor first goes to your health insurance company and says, my patient got hurt, they need surgery, here's why. The insurance company reviews that documentation and then they make a decision. They say, oh yes, the doctor's right, you do have to have surgery. Or they say, no, your doctor is wrong, you should do something else instead. So if they say you're right, you get to go to the hospital and get your surgery. If they say the doctor is wrong, you get a letter explaining why your doctor is wrong. And so as you can imagine, whoa, all right. So as you can imagine, this is not a very popular process for anyone. The patients don't like it, the providers don't like it, the health plans don't actually like it either. So it takes, on average, physicians spend about 2 days a week, or their office spends about 2 days a week on managing prior authorization requests. 93% of physicians say that it leads to a delay in patient care, and about 34% say it's led to an adverse event in their experience for a patient. So let's talk broken leg. I know someone who had a catastrophic injury a while back. And after he had that catastrophic injury, he had to have surgery, pretty extensive surgery to repair it. This process took, so in most cases, this process takes a very long time. In this case, the process itself didn't take long, but there was a long delay in the surgery, which actually meant that there wound up having to be 2 surgeries. That recovery is taking about twice as long as it should, just because of that delay in care. And so this was outside of the prior authorizations problem, but prior authorization leads to this issue a lot of times. There's like, we're talking 2 weeks is what you can wait to get a response, which is a long time to wait. So what are some of the common problems that we see in this process, and why does it take so long? It's 2 weeks to make a decision for a patient that needs a surgery and their doctor says they need a surgery. Sounds like a huge amount of time to wait. The first one is that there's this manual, time-consuming process to submit the request in the first place. Then you have to gather all of the evidence. And we think about it, you don't normally just see one doctor when something's wrong. You go to your PCP, who sends you to a specialist, who sends you to an imaging lab. You get sent to like maybe a phlebotomist to have some blood work done, make sure that you're in good condition for the surgery. All of these are different providers. They all have their own systems. And then your provider's got to gather all that information, put it together in a package and send it over to the insurance company. There's also this problem where the person that's collecting all of this isn't actually the provider. It's somebody that works it's an admin in the provider's office. They're not clinical experts. So they don't actually know always what they're supposed to be gathering. They're just making their best guesses. And so they're often missing things and there has to be this back and forth. You sent me an X-ray, but I actually need an MRI, for example. The next thing is that a lot of the requests are very routine. So I live in a ski area. You'd be amazed how many people break a limb skiing every year. Like you can go talk to any orthopedist, right? And they're like, oh, the laundry list just getting slammed today after the fresh snow sort of thing. And so, you know, they've seen probably, you know, every week after a big snowstorm, they see 15 people that need surgery, same surgery over and over again, but somehow they still have to submit these requests. The next thing is there's also this, so that's kind of like one side, pretty straightforward, simple request happens over and over. Then you have the other end of the spectrum, which are these very complicated requests that do require like someone to look at them, but maybe the patient has underlying conditions or complications. And suddenly we're not talking about like a handful of reports. We might be talking about 200, 300, 600 pages of documentation, especially when we're talking about things where a patient has to be hospitalized and stay in the hospital for an extended period of time. And so you imagine you're the person reviewing this documentation. It's going to take you a while to get through 200 pages of evidence for a patient. So there's a bunch of opportunity areas. So I just picked out some of the kind of superficial opportunity areas. And when we think about automation, like what would be things we wanted to automate? The first one is, as much as it pains me to say, providers send a lot of this information over via fax. And when they send a fax, there's two things that could happen. One is that fax could be representing a new request that we haven't seen before, or the fax could be that additional documentation that was missing before for an existing request. And so you have this intake triage process that has to happen with processing all of the faxes. Then you have a portal where people can just upload documentation, submit their request digitally, but sometimes they miss documentation and you want to come back and let them know automatically, hey, you're missing it. We scanned your documentation. Your MRI report wasn't there. You'll need to add that to get this processed. And the last piece is that you have this opportunity for automating the review process itself on those straightforward requests. A lot of times, you're just looking for some key factors, maybe make sure that the patient doesn't have some warning thing, like maybe they're not an active smoker or they're not morbidly obese, so surgery wouldn't be a big risk. And you could just check this off pretty quickly and get them a straightforward yes or no answer. And so why not automate that as much as possible? So we know we have a problem. We know we have areas for opportunity. Now we actually want to solve the problem. But we're going to pump the brakes for a second. Before I get into that, I'll say, are there any questions about the problem setup itself? Anything unclear? Okay. All right, so solving the problem. Before we jump in and we have a solution right away, there's a couple of challenges that we face with automation. And I'd say that a lot of the AI ML space, we're in these same challenges, right? But in healthcare specifically, I would definitely say, so this is a term from the Army, right? But it's volatile in the sense of if we get it wrong, it can be catastrophic for a patient. So if a patient needs a surgery and doesn't get it, we're talking quality of life. Maybe even if you're talking like a cardiac surgery or something in oncology, it could be whether they live or die. But if you give them a surgery and they're a high risk patient that shouldn't be having a surgery because there's some confounding thing that means that they have a low likelihood of survival or good outcomes, that's also really bad, right? It's very complex. I think there's no question that the healthcare space is complicated. There's a lot of ambiguity. How do you solve the problem? How do you know it's right or wrong? And especially in healthcare, a lot of decisions are being made by clinical experts. And the last one is it's uncertain. Many of the problems that we're trying to solve here haven't actually been solved before. And so there aren't necessarily good tools and resources available. This is not the same thing as building a recommendation engine for which movie or song you want to listen to, right? And so looking kind of in these challenges, there's three major ones that I think we face day to day. The first one is high variability. And when I talk high variability, what I'm talking about is just looking at the patient's medical history. We have about 73,000 ICD-10 codes. So those are the diagnosis codes, and more than 10,000 CPT codes, which are treatment codes. Do a little bit of math, that combination is huge. And obviously they don't all work together, but how do you represent that is a big challenge. The next one is the documentation that gets sent in is highly unstructured. So we always call like documents and image unstructured data. But when we think about like an academic article or a doctor's note, there's a different level of unstructuredness that we're talking about. So here we're not talking that we just have a variety of formats or it's in textual format instead of tabular format. We're talking about like the format of the text on the page varies highly. We have tables, lists, long form text, abbreviations. And generally speaking, each provider has their own formatting. There's not standardization across the board. And the last piece is clinical expertise. So a lot of the decisions that wind up getting made in the review process come down to a clinician's best judgment of the situation. And that clinical expertise is coming from decades, generally speaking, of experience and training, right? They're highly specialized. This is not something that it's easy to teach a person to do. And it's not always readily apparent. Patients are highly variable. And so is their care. So when we look at solving this problem, the first thing that I always jump to, background in operations, is can we make up a process to do it? And so when we think about it, the first thing when we think automation, we say, oh, automation is AI itself. Is it an engineering or a science problem? But automation sounds like that's an engineering problem, right? We just design a better machine to solve this process for us. So really quick refresher for anyone that it's been a while for the engineering process, design process kind of goes through a series of steps. You identify the needs that you're trying to solve. You research potential solutions. You imagine what the solution and the solution state could look like. You make a plan, you build a prototype, you test that prototype, and then you look at ways to improve it. And you keep moving through that cycle. But there's a lot of uncertainty here, right? And the research part, if we kind of like just really say that's probably where a lot of the work in AI and ML happens, then we could think about the scientific method and realize that, okay, in some ways we think data science is a really big title in the field. What's the science part of that data? Come back to the scientific method. And here we're looking at developing a question from an observation, right? Doing research, building a hypothesis, testing that hypothesis, analyzing the results, creating a report, and then going back to ask your next question. This is what scientists do all day, every day. So my suggestion is we can actually take these two processes and put them together. Yes, sorry.
Maybe you answer to the next slide. I'll just wait.
Okay. All right. So my suggestion is we can actually take, and we could look at AI and take the perspective that AI is an actual hybrid of engineering and science. It's not one or the other. And so we can put these two processes together. And what we start to do is we start to see that there's a lot of overlaps or even places where it's completely the same, right? And so we can take identifying needs by asking questions. We're going to stick with research because research is research, right? We can develop hypotheses for potential solutions. We can build and test prototypes. And for us in the AI ML space, prototypes are often models or algorithms. And then finally, we can analyze our results and identify areas for improvement. And so now we have a nice smaller circle. And so I'm going to get into each one of these steps in a bit more detail, but I'll pause and see, do you still have a question?
Does the research that you look for, that you look for, focuses mainly on quantitative data, or do you also collect qualitative data?
Qualitative. It's a blend of both, but where a lot of the focus for my team is on the qualitative data. So we're looking at the clinician's notes. So a little bit of context. You have claims, that's the ICD-10 and CPT codes, right? Diagnosis and procedure codes. On a date, this thing happened for this reason, black and white. But what you're missing there is what the physician actually thought about it. What did they observe? What were their test results? And that's where you get really rich detail in the clinical notes, because now any level of uncertainty or hypotheticals that the clinician's experiencing, or observations that maybe don't map cleanly to a diagnosis and a treatment from a health insurance payer's perspective, that all of that lives in those very rich clinical notes, and that actually gives you the context for a patient. So I'll give an example. One of the health plan requirements for whether or not a patient can have a specific type of surgery is, will mobility be improved after the surgery? What diagnosis or procedure code would you put with that? Right? To know that, like, that is a judgment that somebody has to make. And so what you begin to read is in the notes, the doctor might say, well, the patient has been doing PT, but has limitation and range of motion because of this thing. And they're very motivated. Well, them being motivated definitely has no diagnosis code, right? They're very motivated to improve. And I believe that if they have this surgery, they'll double down on the PT and have exceptional outcomes. Like, that's not something that you're going to ever find in a diagnosis or a procedure code. So we'll go into each of these steps in a little bit more detail, and then I'm going to give you guys a case study. So identifying needs by asking questions. I've put a bunch of example questions up here. The fundamentals of this is you basically want to know, can we solve it with AI or machine learning? And should we do it? And the can we do it and the should we do it are often like at odds with one another. So when we think, can we do it? We're really like, fundamental question, what's the process? How difficult is it to teach a person? How repeatable is it? Should we do it is really around, what are the risks if we get it wrong? And this is a really big one, I think, especially in healthcare, is what happens when we're wrong, and how do we mitigate that risk? How well is the process done today? And what's the cost? If it's cheaper to not do it with AI and ML, then we really have to be critical of why we would do it with AI and ML. The second piece is research. And so this is where I think that academia and industry come together, and we come together in a really powerful way. The first question for research is, how has this been solved in industry? The same problem or similar problems. Not always the same problem in healthcare, but often there are similar problems that you can bring corollaries to. And understanding the strengths and the weaknesses of those solutions. And then you basically do the same thing on the academic side. Read the papers that are related to the problem. What are the foundational theories or solutions? Have there been academic advances that aren't prevalent in industry today that we could potentially use or kind of Frankenstein into our own purposes? And how broadly has this solution been evaluated? I have all the time, my engineers are bringing me papers and they're like, this is amazing, it's so great. And I'm like, it's one paper, or the study size is super small. Can you get some more evidence for why this is going to work? But then from this research, you begin to develop hypotheses for potential solutions, right? You begin to imagine what the solutions are. Here you're generating ideas, imagining your ideal state, but you're not judging anything. You're really just saying like, it's a blue sky, whatever I can imagine could be. Let's think about what those things are. And then you want to start hypothesizing. You want to make sure that you've defined the problem that you're trying to solve clearly, that you're proposing solutions and are articulating the results you expect. And you're really asking yourself, why will this solution work? Why is this a good one to move into prototyping? So then you build and test prototypes. And I think there's, again, 3 places where literature and academia have, and the research come back to play to be really important here. The first one is benchmarking performance. So how well did the model perform in the literature and how well is it performing in the real world? A lot of academic research studies have highly curated data, highly specific, small focused problems. Don't always get to see that in the real world. And so it's an opportunity to compare and contrast. Same thing with benchmarking speed. What were the resources that were used originally to solve this problem or a similar one, or this used to run this algorithm? What are the resources that are available and how do we optimize for those things? And the last one is troubleshooting. So really understanding the details of the study, the constraints of the data that you're working with and the constraints of the data from other projects, and the details of the compute resources that are available. So I'll use the example of large language models because it's ever prevalent in my life today. ChatGPT was trained on billions of documents. We have a few hundred, I think we have maybe like a couple million documents. And if somebody on my team wants to retrain their equivalent large language model, they want to make it equivalent to ChatGPT, I'm like, you can't do that with 2 million documents, right? You have to look at a different solution. Understand those constraints and use them to build better. And then finally, the last piece here, analyzing the results and finding areas to improve. Really, the big question we're asking here is it good enough or do we have to do another iteration? And here we're analyzing the actual performance against our expectations. And we set those expectations, right? When we were doing our hypothesis, we were creating our hypotheses and doing our research. And then we're also looking for ways to improve and how we could implement those improvements. All right, so again, I'll just put this up for a second and see if there's any questions at this point. Yes.
It seems in some ways you can bring a somewhat well-defined problem. Do you find that you need to act or interact with folks outside your team? And, healthcare experts, stakeholders, et cetera, to get some of this information and make sure you can do that correctly?
Yeah, so I think the 2 big areas that this really happens in is identifying the needs and asking questions. And when I say asking questions, you're not just like asking yourself rhetorical questions in your own head. You got to go out and ask questions. And the second piece is in the research. And I kind of talked about industry and academia. I think that there's another place where your research, like call it EDA, but you're researching your own data and you're understanding your own problem space. And this is what I would say is one of the big areas that often gets glossed over. Like, I don't know how many young kids, especially out of college, I've experienced, and they're like, I'll just take all this data and just plug it into a model and then another model and then another model until it works. And I'm like, no, you fundamentally aren't understanding the problem. And the reason I think that that really matters is fundamentally understanding the problem is because there's two big challenges, right? The first one is you're going to have highly inefficient models with all of these extra features that are probably irrelevant. The second thing is you could very well be modeling the wrong thing entirely. Right. I feel as though every kid that goes through the data science program should study causality, right? Because you might be modeling a correlation, but not a causation. And that differentiation, I think, really matters a lot in how reliable your models really are. And when you think about this issue of generalization or scalability, if you're modeling just correlation and not causation, new variables getting introduced could have catastrophic effects. right? And you can monitor a model for that, but it doesn't mean that it's going to be easy to fix when you have the problem.
Oh, sorry, one last question.
Yeah.
Is there times where you found that you really, the amount of questions you could ask was very limited? You know, that like some of that is like setting up the relationship with stakeholders.
Yeah, I have never found that anybody, if you're genuinely interested in their work and their opinions and their thoughts on something, doesn't want to talk about it. But you have to come with a genuine interest, right? You have to kind of take your ego, put it here, and be like, hey, I'm really curious about this process. Tell me what you like about it, what you don't like about it. Where do you struggle? If you could change anything about it, what would it be? Everyone will talk about that stuff. And I think that's actually one of the big, so I'll jump back to Faisal, and he was kind of talking about how kids don't get trained in these programs for this, but it's one of those critical skills because, you know, the reason I say that it's engineering plus science is it's that scientific method, right? That's what scientists are really good at, is they're just boundlessly curious. And that curiosity becomes like this, nothing else matters besides the curiosity and the questions. And I think it's that same attitude. If you want to be really successful in the AI space, you have to have is that same level of curiosity. Yeah.
Good question about the diagram.
Mhm.
What stage is the product, the final product? Would that be the prototype perhaps, or does it come after analyzing the results? Where do you?
I would put it after analyzing the results. So you have a prototype, but if you haven't analyzed the performance of that prototype, I don't think you have a product yet, right? And so where I will say our product teams are generally, when I work with a product team, I try to have them involved in every step of this process. Because first, the product team is going to tell me, like, is this thing, do we really have a need here? And do I understand the need correctly from the business context? Then when I'm researching the problem, I need to understand what they need solved, like, and how they need it solved. And when I'm developing hypotheses for solutions, I want to make sure that those solutions are aligned with their expectations. And we're circling back to that needs problem. Building and testing prototypes, we're talking about like how we would actually implement it and what could happen there. And when we're analyzing results, that question of, is it good enough? I don't know. I've never met a statistician or a data scientist where I said, was it good enough? And their answer was ever yes. Like, not until they got to like a certain level of experience, maybe, but like generally speaking, they're like, oh, well, I could make it just a little bit better if I could just have one more week, right? But a product person is going to say like, yes, this is good enough. We're satisfied with this from a business perspective. Now you can implement it. Yeah.
Well, this might be a little bit of a philosophical question, so we can take it offline if you prefer. Yesterday, Faisal also mentioned the risk of private data being better than public data because you have your private proprietary data. And here you're looking at making a system that's going to hopefully assist, if not replace, some of the manual human pre-authorization method of the machine.
Yeah.
Where do you see your company or yourself as having a moral obligation to share what you learn so that the rest of your competitors, frankly, can make decisions that are in the best interest of the human who is behind this?
Well, I think you can do that without sharing data, if that makes sense. So when I think about like a process like this, and so there's kind of two pieces to the coin. There's one piece of the coin that's the business implementation. And that is really private and specific to your company, because to be as effective as possible, it's got to meld with your business practices. And that is going to, frankly, be unique from organization to organization. But on the other hand, you have the core algorithms and ideas that you're developing. So for example, I'm going to go through an example here about faxes. But if you think about like OCR is a very good example, where optical character recognition is a broad use application that could be used to solve a lot of problems in a lot of industries. If you were just developing your own proprietary in-house OCR application, I don't think you're doing anybody any good, not even yourself, right? But if you're contributing to an open source project, or you're supporting a broadly available application or function, that's a completely different scenario in which you're driving the entire field forward. So that, yeah, okay. But yeah, the data, sadly, the data is just something that we can't share for privacy reasons. I wouldn't want my data. I already feel like too much of my data gets used by companies, personally. Okay, so I'm going to jump into a case study here and kind of talk through one example of how we've used this process. So fax processing, as I mentioned, is one of the big challenges. So put some generalized hypothetical numbers in here, but let's say we do 1,000 faxes a month and it takes about 10 minutes to process a fax. And this costs us $5,000 a month, roll it out at $60,000 a year. Maybe not a huge cost for a small company, but if you're growing, it gets to be a bigger cost, or if you're part of a very large organization, could be a huge cost, right? That you could add some more zeros onto that 5,000 a month. So we start with this first, identify needs by asking questions. So maybe our first question is, what's the current process? And we build out this process tree. So we get a fax, we check it, we look up the patient, we look for existing request. If one exists, we attach it. If one doesn't exist, we create a new request and fill in those details. Pretty straightforward process. How difficult is it to teach a person to do? Well, it's pretty darned easy. That seems like it's a pretty good candidate for automation. How repeatable is it? Super repeatable process. Not a lot of exceptions that are going to happen here. What are the risks if we get it wrong? So we might miss a request, right? So instead of creating a new request, we attach it to an existing one and we miss that there's a new request for the same patient. The second thing that we might do is create a duplicated request. So in the first instance, maybe a patient their authorization never gets processed. That's pretty bad, right? But in the second scenario, we've just created more work for ourselves, which is also kind of bad, but maybe not the worst thing ever. How well is the process done today? Done pretty well. People get it right most of the time. And what's the cost of the process? That's about $5 a fax. So getting it wrong, kind of not too bad. So then we go out and we do research and we say, okay, what are some potential solutions? So use an example. We were using Tesseract, which is a leading open source OCR platform. There's another solution for OCR called AWS Textract. OCR just stands for optical character recognition. So this is taking an image and converting it to text. What's the difference? Tesseract is the leading open source solution, so it's free. Cool. AWS Textract is a platform supported vended solution, which means we're going to have to pay for it, but maybe it's got better performance. So after we do some research, we learn more about these platforms, we begin to develop some hypotheses for the solutions themselves. So on the Tesseract side of the room, we've got this idea that we're going to have better control. Because it's open source, we can contribute to the open source project and we can fine tune the algorithm. We can speed it up, slow it down, turn it sideways, whatever we want to do with it. We also have this hypothesis that it will be lower cost because it's not a vended solution. So yes, we're hosting it, but still hosting it should be cheaper than paying AWS. On the AWS side of things, our hypothesis is they're charging money for it, so it must do a better job. So improved quality. They have another service called Key Value Query, which could mean that, hey, maybe we can write a whole lot less algorithms and just use that. And then the last piece is that it will actually allow us faster inference. So when we send a document in, AWS will give us a result faster than if we just ran Tesseract ourselves. So we're going to build and test some prototypes. So for us, we already had Tesseract up and running. So it was easy enough to set up some additional monitors and logs to capture all of our evaluation criteria. On the AWS side, we had to set up a dev system for testing, as well as the monitors and logs associated with it. And then we get to analyze results. So here we begin to see like our hypotheses are confirmed. Most of the case, except for AWS Textract, we don't get faster inference. Now, depending on your business case, this could be a big problem or a little problem, right? For us, it was a big problem, but we managed to work with AWS to get it resolved. And so kind of go through this process, right? So we say, okay, hey, when we get to the end of this, faster inference, we have to have faster inference. It's not fast enough. So this is our point to go back through that circle again, right? And say, okay, how can we improve the inference speed for Textract if it's giving us this improved quality and improved key value query? And yes, Tesseract's lower cost, but we're willing to sacrifice some of that for the improvements that we're getting over here. That was a very fast kind of demo. All right, so I'm going to go through a conclusion. So basically, this process is one that you can follow, but there's a bunch of reasons why it's super useful. The first one is it leads to innovation. So by taking the time to do the research and think about solutions and build hypotheses and really forcing data scientists and machine learning engineers to slow down and think about these things, they come up with new and out of the box ideas. The second one is increased engagement. It's really easy for people to go onto autopilot, and this causes them to stop and engage Also innovation. So it's a really interesting thing in a lot of HR studies, but they've seen that innovation and engagement are actually linked to each other. So the more engaged people are, the more innovative they are. And that cycle just keeps, and the more innovation that's happening, the more engaged they get because it's exciting and fun, right? And so following a process like this gives people a framework to help this happen. The next thing, and this is really huge, I think, from a business perspective, is it brings transparency to the machine learning, AI, data science process. And it gives you a framework that you can use to discuss what's going on, what your teams are actively doing with the rest of the business. It also gives you control over scope and time creep. So when you start to think about each of these steps in the process, you can start time bounding them. You can say, okay, we're going to spend the next month identifying needs and asking questions. At the end of this month, we need to make a decision. Do we know enough about this problem to keep moving forward, or should we stop this and work on something else? Same thing for research, same thing for developing your hypotheses. And maybe it's not a month, maybe it's a quarter, maybe it's a year, but as a business and as a leader, you get to make that decision. And the last piece is it allows you, and it enables you to build alignment across stakeholders. When you start to be able to bring transparency to your processes, you begin to control scope and time creep. You're also doing that, right, by being more connected with the business and building out that alignment. And so that really helps to avoid the issue. I don't know how many of you have had this. Feel free to raise your hands. You build something and then the business says, well, that's really nice, but I don't know what we're going to do with it. It's very disappointing when that happens, right? And it's really difficult as a leader if you have a junior employee that does that, and then because they're so excited about what they did, and you're like, yeah, but nobody wants what you did. I'm sorry, right? So having this process and having key places where your stakeholders are engaging means that you avoid some of that problem, and you're actually focusing on not just what's cool and shiny, but what's practical and useful inside of the business. All right, so that's everything I had. Any questions that I can answer? Yes.
One of the topics, when you listed the,
This one?
Yeah, exactly.
Okay.
In number 3, when you listed transparency to the, AI, so one of the things that's related to transparency is explainability, like how your AI actually reached the decision, for example. So how do you tackle explainability, or is it like one of the criteria that designers?
Yeah, so what I find is that, so I'm a very big believer in the idea that you have to understand the problem first. And when you understand the problem, it means that you're selective about the features of the information that you're feeding into the model. And so the way I look at explainability is and I've never met a business person that really likes this, right? I don't want to explain how the algorithm is working. What I want to explain is what I'm giving the algorithm to make its decisions and why those are the things. So if I say, okay, I'm going to, OCRs may be a bit of a black box, so maybe that one's not so great, but let's say that I'm going to build a regressor to predict patient costs. And in that regressor, I want to include pre-existing conditions. Well, why do I want to include pre-existing conditions? That's because we know that patients with some pre-existing conditions will have to have routine medical care, and that will drive up their costs, right? And so then a business person understands that, and to them that's explainable. They're like, okay, I get it, right? That makes sense why that's something that you're accounting for in your model. Any other questions? Yeah. Yeah.
So, see the potential solutions. I think part of that a comfortable conversation we were talking about with business, right? Is I force my analysts to have this conversation. Okay, now that we've developed our hypotheses, you, the business stakeholder, what are you going to do differently? Improve it positively, improve it negatively, or we actually come up with something that's always been inclusive, right? And if you don't have an answer as a business to all 3 of those branches, we're not going to proceed and actually develop a prototype or do the analysis, so we'll waste a lot of time.
Yeah, no, and I think that's a very good point. And so one of the things that I tell internally to my business stakeholders and my team is that this whole thing can fall apart at any step in this process, especially the hypotheses and potential solutions. That's probably where I'd say most things do wind up falling apart, is because of what you're talking about, and because you start making these hypotheses and these potential solutions. And then when you say like, okay, what should go to prototyping, you start just, everything gets X'd off, right? And you're like, none of this should go to prototyping. It's all garbage. And so there's this really big question of like, hey, if we can't solve this, then like, why are we even trying to? It's a really difficult question. So I feel as though there are generally two classes of people, the ones that are super excited about AI and the ones that hate it, right? And for the ones that hate it, this is kind of easier because at least it gives you a framework to bring them on a journey with you and make them more comfortable. But for the people that are super excited about it, I actually think a lot of times they're much more difficult to deal with because when you try to ground them, they get upset, right? And they're like, don't hold me back. Don't tell me we can't solve this with AI. And it's like, well, the technology's not here. We haven't collected the appropriate data as a business. And that's a really hard thing for people to hear. It's like, I want to eat the cake. And it's like, well, we're not going to have any cake because we have to harvest the wheat first. I'm sorry, you know? Yeah. Yeah, I've worked on some really silly problems in the past where somebody wanted, like I worked on a problem where this product manager really had it in their head that they wanted us to predict when somebody would need to refill their fuel tank. And I'm like, it's on the car. It's engaged on a car, right? Like every time you get into the car, you see it. And when it's really time, there's a light that turns on. Like we don't need a model for this. But to say that like it's not something worth modeling is often a really difficult conversation to have for people that are excited. Yeah.
Something unrelated to you mentioned something about
Yeah.
So that means that
yeah, and it's actually interestingly enough, it's not just ChatGPT. We don't even have an embeddings model. So there's BERT, right? That really popular embeddings model. And there's another version of BERT called BioBERT that was trained on biomedical texts. And when they say biomedical texts, what they mean is academic journal articles for clinical research. But if you think about real clinicians' notes about real patients, that's all private data. None of that is public. And so none of these big language models, even something as basic as like BERT or BioBERT embeddings models, none of it's been trained on that data. And where I use the analogy of like why this is problematic in the healthcare space, SOB. We all know what that means in everyday language, right? I don't have to say it, SOB. In healthcare, that means shortness of breath.
I thought it meant statement.
Or it could mean statement of benefits, right? But like, if we're talking like everyday street language, SOB doesn't mean either one of those things. That's highly contextual, what it means. And if we're thinking, and so if we take BERT and then we build a model with BERT, is it going to get shortness of breath, or is it going to get statement of benefits, or is it going to get the other one? Don't know, but I can tell you it doesn't often get shortness of breath, right? We have that with we've gone through with a lot of these models, both things like like the large language models like ChatGPT and other things, to be like, okay, let's just give it some synthetic data that we've made up. And we'll say like, can you pull all of the blood urea and nitrogen levels? Can you pull all the blood pressures? Sometimes. Can you pull all of this? And it's really hit or miss on what it is or isn't capable of doing. So that's one problem, is just that the language and the context necessary to train the model isn't present. The second problem is going to circle back to what I talked about, where all of the documents are in different formats. So most of these models were trained with this idea that people write coherent sentences and paragraphs where there's a specific structure that we follow in the English language. But when you start putting tables and forms and lists and shorthand and fragmented sentences in, suddenly doesn't know what to do with any of it. And that's what a lot of these clinical documents are, is you might get a table and the field labeling, like the label for the field and the field data is this like above and below or below and above, right? Side to side, the other side around. Sometimes it's just a statement and then it's a bunch of numbers and you just circle a number, right? When we're thinking test results, these are all, and so when you ask one of these models to do this, that's not how they're used to seeing. Even something like ChatGPT that's been fed tons and tons of data, it looks at right? That's what all of our models are doing. They're looking at the median, it's looking at, or the average, it's looking at where the most happens, not the outliers. And what we wind up dealing with in healthcare is a lot of outliers. Up to like 30% of the data would fall into the field of like, it just doesn't work.
So, yeah, I wonder if, right now, I mean, it hasn't been done yet, but I wonder if they'll, some research lab somewhere, they're looking into something similar to transfer learning. Where you can,
Yeah.
attach like a smaller data set on there and sort of put more weight on that. And I know that was popular, like, 5 years ago or something, before starting to use it for other, generative AI, but I
Yeah,
wonder if there'll be something like that.
I think so. So we've looked into, so you can do transformer heads, which is nice. You can do parameter efficient fine tuning, which I think somebody else talked about earlier yesterday. And then you also have the opportunity to take a lot of what's amazing is like ChatGPT kind of blowing up has really blown open the space and made a lot of people excited and like double down on working on these algorithms. And so we're starting to get very powerful, smaller language models. And so you can take one of those small language models, fine tune it pretty quickly with parameter efficient fine tuning and get decent results. And so that's a lot of what we're looking into now to kind of overcome some of these problems. Yeah.
But I'll ask the same question.
Okay.
I have one more. So the case study that you presented, or in general for your company, how do you explore federated learning as a tool, for example?
Figurative learning?
Federated learning.
Oh, federated learning. Not so much. Yeah.
That's curious.
Yeah, no, we haven't yet. Who knows? I'm constantly pushing. I think that that's one of the things that's so amazing about the field is like, it feels as though every year it does this and it's just like expanding so fast. So it's where I try to push on my team members to try something. We actually go through these design cycles. So during the develop hypotheses, we might have 1 or 2 or 3 people working on the first 2 steps and then developing hypotheses. I'll take the whole department, which is about 20 people, and we'll sit down for a day. The people that have been doing the research will present it, and then they'll come up with solutions that they think might work. And often we'll do like a hackathon and everybody will try. So we'll like vote on the best solutions. They'll break into small groups and try them out. And so we might have like 5 or 6 completely different modeling or algorithmic paradigms that we're pursuing to see what's going to actually work. Because you'll think about a problem and you'll be like, oh, QA model will solve that. It doesn't solve it. And we run into that with a lot of stuff where it's like, oh yeah, this will totally get it. And it's like, okay, well, who's in that camp? Why don't you guys go work on that problem? And then somebody else will come up with a different solution. They're like, oh no, I can solve this all with a regex. Okay, well, who's in that camp? Go sit over there, right? And so it's an interesting kind of dynamic, but it means that we get to try stuff out, but we haven't gotten into federated learning yet. Yeah. So they are not letting people use them yet. We've been talking to them. They're not letting people use them. The last time we talked to them, they weren't comfortable with their performance. So yeah. Yeah, because I'm a big believer if we can buy it, why would we build it? And there's some like resources that companies like Amazon and Google have are just so far beyond what we could ever build. What's interesting is we've John Snow Labs has like a whole healthcare NLP thing, and we've gone up against them a couple of times and still outperform. So I think that it's also has to do with being smart, not necessarily shady in what you're doing to get good performance.
For that one, is it, do you think that's because you have better data, or do you think it was more like the algorithm piece?
That's a good question.
Not that
I don't know. So I don't know underlying what their algorithms are. So it's hard for me to say for sure, but I suspect that it has something to do with the broadness of the scope of data that we're exposed to, and that they had a more, because what their failure point was the same thing as like that we've seen with other large language models in general, is that their failure, it's like they do great in certain scenarios, but in other scenarios they completely fail. And John Snow Labs is kind of that way as well, where it's like, okay, you're doing pretty good here, but here, and here, it's horrible. And that's not going to work. Any other questions? I know we're a couple, 5 minutes over. Want to go eat lunch? All right, thank you so much for your time and attention.